Okay. All right. So in my last talk, I didn't give any proofs, and like it was like just like theorems and statements. But in this talk, I'll try to give some proofs which are not like too complicated. Okay. So first, I'll start with orthogonal polynomials on the real line. So first, we'll define what are orthogonal polynomials. So suppose we have a positive measure on R, and we assume that all the moments are finite. Since L2 R d mu is a vector space with basis 1 x square, all the monomials, we can apply the Gram-Schmidt process to obtain the monic orthogonal polynomials, right? We can apply Gram-Schmidt process to get these polynomials. So I'll give the name that nth orthogonal polynomial is pi nx. And it obviously satisfies this orthogonality conditions. It can be shown that the pi-n's are unique. Yeah, but I'll not go into that. Okay, we'll make an additional assumption on the support of mu. We'll assume that it is supported on infinite set of points. Because when mu is supported on infinite set of points, this vector space is infinite dimensional vector space. And in particular, this will imply that the set of orthogonal polynomials is infinite. One can show that if mu is supported on, say, finite number of points, then you will get only finitely number of orthogonal polynomials. So this is just an additional assumption. Okay, now we can define an orthonormal polynomials, P and X, which will be a multiple of the monic orthogonal polynomial. And since it is orthonormal, it obviously satisfies this relation. All right. So now we'll try to give two formulas for this orthogonal polynomials. Okay, so we have to introduce some determinant, which you might have heard something known as Hankel determinants. So let's define this Hankel determinant. So h of n is given by determinant of where the entries are integrals over s, and the function is s to the power I plus j. And this is how it looks like. So at any point, if you go to the right or go to the bottom, we increase the power by 1. And this is called the Hankel determinant associated with d mu. Okay, for later purpose, I will not write this s, and I will not write r, because yeah, it's understood that this is r and s. So we'll use this Hankel determinant to produce orthogonal polynomials. Okay, this determinant has a closed formula. Yeah, you can check on the Google, but there's something formula known as Andreev's determinant identity. One can use this to show that this determinant is nothing but this integral, 1 over n plus 1 factorial, and this is n plus 1 integral of this function. So if you see this integrand, this is nothing but the van der Waals determinant square. So this is a square of van der Waals determinant. The next thing to note that this determinant is always positive. This is true because of our assumption that mu is supported on infinitely number of points. It's not like obvious to show that, but if you assume that if mu is supported on infinite number of points, then this determinant will be positive. Okay, so we have defined a determinant which is always positive. Now we'll define a function h and x, which is similar to the Hankel determinant. What I'll do, I'll just erase the last row of this determinant and replace it with 1x and x to the power n. It's just that. I have just replaced the last row by the monomials. Of course, you can guess that I'll show that these are the orthogonal polynomials. Okay, first of all, if we want to show that some collection of polynomials are orthogonal, we want to show that P and x, the integral of P and x, P and m, Pmx should be 0. But instead of that, you can show that for every like n, P and x, if you integrate with the monomials 1x, x to the power n minus 1, it will be 0. So that's what I'm going to show. That for any k between 0 and n minus 1, if you integrate xk and h and x, then this will be 0. Okay, now let's try to imagine how we'll integrate this. So I'm integrating this hnx with x to the power k. Okay, suppose you expand this determinant, right? You expand this determinant, you have some polynomial in in x, and then you're integrating with respect to x. So what will happen? All these entries will get integrated, and you will get this, right? This one become x to the k, this will become x to the k plus 1, and x to the k plus n. This is what it becomes. So this integral is nothing but this. Now, as you can see, that since k is less than n minus 1, two rows are the same, and hence this determinant should be 0. So we have seen that for all x to the power k, this inner product is 0. In particular, it implies that hnx satisfies the orthogonality condition, right? Because without loss of generality, you can assume that n is less than m, and then hnx is like a linear combination of 1x up to x over n, and each of them is 0, and so hence this is 0. So we have shown that hnx satisfies the orthogonality condition. But eventually, I want to get orthonormal polynomials. So let's try to find the norm of hnx. Okay. So note that the coefficient of x to the power n in hnx, that means the leading power, the leading coefficient, is nothing but the n minus 1th Hankel determinant. So let's go back and see. So when you expand along the last row, you will see that you will erase these two columns, and the leftover thing is nothing but hn minus 1. So the leading coefficient of hn is hn minus 1. Okay. This happened last time also. Oh no. Sorry.
बंद करके फिर सबको ओपन करो.
Close everything. Just okay. Hopefully, now it will work. Okay. So note that the coefficient of x to the power n in nth orthogonal polynomial is hn minus 1. Now I want to integrate this hnx square. But as we have noticed that the integral of hnx with monomials which have power less than n will be 0. So one of hnx I can just write as hn minus 1 x to the power n, because the rest of the terms will integrate to 0, right? And then since hn minus 1 is a constant, it goes outside. And this is nothing but, this is like similar to the last part. So you're integrating with respect to x over n. So when you do that, oh no, why is this happening? The last row will become exactly this. And so this is nothing but hn minus 1 times hn. So if you know the norm, I just have to divide by that. Now these are the orthonormal polynomials. So Pnx is this 1 over square root of norm times hnx. And as we know that the leading coefficient is hn, if you do that, like if you just write like that, you will get this. And so this is your nth orthonormal polynomial. We defined earlier that gamma n is the leading coefficient of orthonormal polynomial, which is given by this. So we have a specific formula, like the explicit formula for the orthonormal polynomials. Second formula is just to expand a determinant. One can write this hnx like this. One can show that this pnx is nothing but this. So we have explicit formulas for the nth orthonormal polynomial. So first we define what are orthonormal polynomials. We have given some formulas. Now let's see some properties. Okay, so there's a three-term recurrence relation that orthonormal polynomials satisfy, which is given by this. So x times Pnx is a linear combination of Pn minus 1, Pn, and Pn plus 1. And for n equals to 0, it's slightly different. Okay, this is like actually very easy to prove. So what do? Pnx is a polynomial of degree n. If you multiply by x, it will become a polynomial of degree n plus 1. And orthonormal polynomials form the basis. Since this is a polynomial of degree n plus 1, you can write it as a linear combination of p0, p1 up to pn plus 1. And just using the orthogonality conditions, you can show that the coefficients, the rest of the coefficients will be 0. And you can easily show that this coefficient bn is gamma n over gamma n plus 1. Gamma n, remember, is the leading coefficient of orthonormal polynomial. Ans are a little bit difficult to find, but they can also explicitly be found. Okay, now one can show that all the roots of orthonormal polynomials are real and simple. The multiplicity is 1, and they're all real. So how do we do that? So let us define a set R. So this is collection of all real roots of Pn such that Pn changes its sign as those points, which is equivalent to say that it is the set of all real roots of Pn such that the multiplicity is odd. So first I'll show that this set is non-empty. Since Pn's are orthogonal and P0 is 1, so P0, inner product of P0 with Pn should be 0. So we know that this should be 0. This implies that it cannot always be positive or always be negative. There should be a point where it should change sign. So we know that R is non-empty. Now I have to show that R is exactly n. Okay, now I assume that R is given by R1 up to Rm, and I assume that m is less than n. I'll show it by contradiction. So these are only the points where Pn changes its sign, and these are the zeros. Now we consider a polynomial Qx, which is x minus R1 up to x minus Rm. What will happen if I multiply this Qx and Pnx? So these are all the roots where the multiplicity is odd, right? And if I multiply by Qx, those will also become even. This will imply that Px times Qx will always be positive, right? And then you can show that this integral is always positive. But this is a contradiction, right? Because m is less than n. The integral of Pnx with any polynomial whose degree is less than n has to be 0. So we have a contradiction, and that means that m is equals to n. And that in particular implies that all the roots are real and simple because they change sign at those points. There's another useful formula for the useful relation between the orthonormal polynomials. So if you take this summation, the product of Pix, Piy, and sum it over from 0 to n minus 1, one can show that this is equals to this. And this is also not difficult to prove. What you do, you cross multiply this. So you cross multiply x minus y with this. This will become x Pix Piy minus Pix y Piy. Now we know that x Pix, if you remember, you have a recurrence relation, right? X Pix can be written like this. And so you use this relation and it just follows from there. Okay, another property is that roots of Pn minus 1 interlace with the roots of Pn. That means if you have two consecutive roots of Pn, there always lies a root of Pn minus 1 in between. So let's show how this follows. Okay, this relation, as you can see, is for x when x is not equals to y. But you can easily take limits, and you can show that for x equals to y, when you take x equals to y, this right-hand side becomes this Pn prime x, Pn minus 1x minus Pn minus 1 prime x, Pn x. So right-hand side becomes this, and left-hand side is obviously the sum of Pix square. Summation of Pix square is always positive, and hence the right-hand side is always positive. So we'll use this relation to deduce that the root lies between the two roots. So I assume that if a and b are two consecutive roots of Pn, then I plug in a here. So I get Pn prime a, Pn minus a, Pn minus 1 prime a, Pn a. Pn a is 0. So that means Pn prime a, Pn minus a is 0, is greater than 0, and this is greater than 0. Okay. What can you say about the signs of Pn prime a and Pn prime b? Since there are n simple roots, we can say that the signs are different. The sign of Pn prime a and the sign of Pn prime b, like of course they are non-zero, and they have different signs. That implies that the sign of Pn minus a and Pn minus b are different signs. So if you have a polynomial and at 2 points they have different signs, it must have been that it crosses the real axis. Implies that there is at least one root of Pn minus 1 in that interval. But it happens for every 2 consecutive roots. So just by counting, you can conclude that there cannot be more than one root, and hence there is exactly one root. So these are all the properties. We have seen a recurrence relation. We have seen the roots of orthogonal polynomials are real and simple, and this last property. Okay, I didn't give examples until now because I was not going to prove them, but let's see some classical orthogonal polynomials, which actually occur in like mathematical physics a lot, and also in quantum mechanics. Might have heard like, yeah.
Yeah, so how are you saying there is exactly one root? I mean, what about the endpoints?
Yeah, so suppose, so Pn minus 1 has, one, okay, it works. Pn minus 1 has n roots, right? Can you hear me?
Yeah.
Hello? Okay. So R2, R3, and Rn minus 1. And Pn minus 1 has exactly n minus 1 roots, right? I've shown that between any two, there are at least one. But it cannot be more than one, right? Because just by counting. So suppose in between here are, I don't know, k1 number of roots, k2 number of roots, and kn minus 1 number of roots. So the sum of these should be n minus 1. So that means all these k1 up to kn minus 1 should be 1. Do you see that? Okay.
But can't they be before R1 and after?
Like before R1 and Rn, you are saying?
After Rn?
After Rn, there will be no roots of
Okay.
Pn minus 1, yeah.
Okay.
So between every two root, there is one root. And since there are n roots of Pn minus 1, and between every two there is one, if you see just by counting, it should be n minus 1, and which is okay. Okay, I'm not going to prove this, but you might have heard Hermite polynomials. I think everyone has heard, but these are some classical orthogonal polynomials used in mathematical physics, and these actually occur in random matrix theory. So corresponding to different ensembles, we see Laguerre polynomials, Hermite polynomials, and Jacobi polynomials. So what are Jacobi polynomials? So we fix parameters alpha and beta, which are greater than -1, and we take the weight function, which looks like this, and it is supported on -1 to 1. Similarly, for a parameter alpha, there's a weight function corresponding to which there are Laguerre polynomials. The one which we're interested in is the Hermite polynomials. And these are orthonormal polynomials with respect to weight, which is given by this, e to the minus x squared. Okay, why did I do this the bunch of orthogonal polynomials? Because this will occur in unitary invariant ensembles. So next I'll go into that.
Hey,
So
can I
remember
ask a
last,
question?
yeah,
So this requirement that the set should be infinite,
yeah, the
how,
set
I
the
mean the
measure should be
points.
infinite.
Yeah.
Huh.
Okay. So how does that affect if you change it to like just finite?
So suppose mu is supported on say endpoints. Like
Mhm.
suppose that mu
Mhm.
is supported at endpoints like x1, x2, xn. If you take any other set which does not contain this point, the measure is 0. Then you will only get polynomials up to Pn. You won't get. Yeah, the thing is like in this mathematical statistical physics or mathematical physics, what you want to do, we want to study the large asymptotics, right? Like what happens as n goes to infinity. So we require that there should be like infinite number of polynomials.
I see. Okay. Okay.
And so since these polynomials occur in mathematical physics and we always try to find it asymptotics, we need them to like be infinite.
Okay. And all the things that like reconciliation and everything like sort of fails, right? Because you don't have that integral condition greater than 0. It can be greater than or equal to 0. So sign change and everything is also affected, right?
Which part? I didn't get that.
When all these things like your basic assumption was that because of that condition, you have that the integral is positive, never 0.
Yeah, the Hankel determinant is Hn is positive. Yeah.
Yeah, exactly, right? So if it
Yeah.
was finite, probably that will be 0 at some points.
Right. Yeah. Yeah. So after some point, there will be no orthogonal polynomials.
Because the currently I'm using Hermite polynomials, and there are some
Oh,
sequences of finite polynomials that actually converge to Hermite polynomials in limit.
okay. Okay.
Yeah.
Okay.
So I was just thinking like, how does that? Yeah. Basically, I have to show that certain polynomial after some point become positive, like have positive Hankel determinant, I guess.
Oh, okay. Okay.
Yes.
Yeah. So the measure is supported on infinite number of points because we need infinite set of polynomials. Okay. Now let's see. And now we'll define what are unitary invariant assembles. So remember, every probability space or measure space has a set, a sigma algebra, and a probability, right? So the set here is n cross n Hermitian matrices. This is our set. And the probability measure is given by this. 1 over Zn e to the power minus n trace of V of m dm. Zn is to make sure that this is a probability measure, that when you integrate this part, you will get 1. This is to ensure that this is a probability measure. And what is this dm? Dm is just the Lebesgue measure of the entries. So if you have a Hermitian matrix, its dimension will be n square, corresponding to the real part of off-diagonal entries, imaginary part of off-diagonal entries, and the diagonal part of off-diagonal entries. So this is just the product of Lebesgue measure. This is very simple measure. Okay. What is V here? So this measure is characterized by a function V, which we call potential because it occurs in potential theory as well. So this is called the potential. And the conditions are to ensure that like that this Zn is when defined. So you want that this Vn goes to infinity at a rapid space, so that this integral is finite. And that's all we need. Okay. For polynomials, you can define what is V of m, right? So if V of x is say x squared, then what V of m is just m squared. But using spectral theory, like we have a spectral theorem, right? That if m is Hermitian, then there exists u unitary such that I can write m as u du d star. Then by definition, what is Vm? V of m is just u. I just apply v to the diagonal entries and u star. This is how Vm is defined. Is this clear? How do we define Vm? So we have a spectral decomposition and we apply v to d and then u v d u star. Last time I showed that why these are called unitary invariant ensembles. So these are called unitary ensembles because if you take a unitary matrix, conjugate by unitary matrix, the measure remains the same. Okay, so this is the definition. What do we do of random matrix? We try to study its eigenvalues. Again, so since M is Hermitian, we know that eigenvalues are real, which are x1, x2, xn. Then one can show that the joint distribution is given by this. 1 over Zn prime. This is nothing but the van der Waals determinant square. And this is product of e to the minus n vxk dxk. Okay, so what does this first factor ensures? So if you see at the first factor, it tells that the density is small if the eigenvalues are close to each other. So this forces that the eigenvalues are not close to each other. The other part says that xk cannot be very, very large because vxk goes to infinity. So these are all confined, yet they are spaced. So I give this a name that, let us say that this function is x1, this function is given by p. Okay, now I'll try to like prove that it has a determinantal structure. So you can see that this is nothing but a van der Waals determinant square. So this can be written as determinant 1, right? This is nothing but a van der Waals determinant. And I can take it transpose. Okay, now important observation. I don't want to like use this form. I want to do something else. Once it shows up, बदरी बेइज्जती हो रही है.
वन नोट बंद करके फिर से ऑन करो. होता है ये, पता नहीं क्या नाटक है. रिसेंटली ऑन किया है.
वेट करो, ऐसे खोल के वेट करो, देखता है.
Okay, I can tell what do we do after this. So we do not want to use this sort of matrix. So we know that determinant is unchanged if we add a multiples of rows or columns. Okay, so I'll take the last column here and I'll multiply, like I'll add the multiples of last n minus 1 rows, right? And we can form any monic polynomial of degree n minus 1, right? I can just add the multiples of the last n minus 1 rows. Similarly, after I do that, I can add like from the last column, I will go backwards. And all these entries, I can form some polynomials. And this is, remember that this will be monic polynomials. I can multiply and divide by to make it any polynomial. So this in fact holds for any polynomials. So by row and column operations, since we know that determinant is unchanged, what I can do, I didn't want to write this whole thing again. You can show that this determinant is nothing but this, where pk minus 1 are polynomials of degree k minus 1. Similarly here, you can add the rows, where p and x is a polynomial whose leading coefficient is gamma n, and that's why I have divided by this product. So this is a huge liberty of like introducing any polynomial, and you know what polynomial I'm going to introduce. It's going to be orthogonal polynomials. Okay, so now there are some calculations. So I know that p of x1, x2, xn is 1 over zn double prime. I've absorbed these two factors in this normalizing constant. Determinant pk minus 1 xj, determinant of pj minus 1 xk, and this another factor. What I'll do, I will do half and half and distribute here. So determinant of A, determinant of B is nothing but determinant of AB. Yeah, remember, so Zn double prime is nothing but Zn prime product of these. And Kn, the j comma kth entry is given by this Kn xy. It is e to the power minus half n vx, e to the power minus half n vy, this summation. Have you seen this summation before? So this is the Christopher Dabu formula, and that's what we're going to use here. So now what we do, we interpret wx is equals to this as a weight function, and we choose pk can be any polynomial, but I'll choose them to be the orthonormal polynomial with respect to this weight. Okay, it's not difficult to show that it's a reproducing kernel, and it satisfies this property for any polynomial p which has degree less than n minus 1. And in particular, this implies that Kn satisfies this relation, that if you integrate Kn xz, Kn zy with respect to z, then you get Kn xy. All right. Okay. So how do we want to study these eigenvalues? We'll define something known as correlation functions, which are given by this. So the nth correlation function is proportional to the marginal distribution for a group of n eigenvalues. So how do we get the marginal distribution? We just integrate on those variables, and it's defined by this formula. So this part is nothing but the marginal distribution, and this is the proportionality constant. Okay, let's try to see what do these mean and what can we do with this. So first I'll take n is equals to 1, and then I will do it for general n. So let's take any measurable set I in R, and we will integrate this function. So when I take small n equals to 1, this will become n, and that's what it is. And then I'm integrating with respect to I with dx1. And if you see, this part is nothing but the expectation of indicator function on x1, right? You can just bring this I, and you can write as R p x1 up to xn 1 I x1, and then dx1 dx2 dxn. This is how we define, right? Expectation of f is f if density is say dx, not dx, let's say something wx, and this is how we define expectation. So this is nothing but expectation of 1i x1. Okay, now another thing to observe, that this density function, this p, is symmetric in x1 x2 xn. So you can write this n times this as summation of I from 1 to n expectation 1xi, because all of them are identical. Then you can take the summation inside, and if you see, this is nothing but the number of eigenvalues which lie in that interval. More generally, you can do the same thing. If you take 1 over n factorial, integrate the nth correlation function, there's some constant. Oh, I forgot to write p here. Similarly, you can show that this integral part is nothing but the expectation that of the indicator function that the first n polynomials lie in this interval. But again, due to fact that p is symmetric, I can write this as summation over all n collections of eigenvalues of this. Then you take the summation inside, which gives expectation that the number of n tuples of eigenvalues is in I. More can be done with these correlation functions, and actually it suffices to study these correlation functions. Okay, so now my aim is to somehow simplify these correlation functions. It looks like some integral and some. Sorry for this. बदरी लैपटॉप में इज्जत उतार रहा है. Okay. So next, what I want to do is to simplify this formula, because that's what suffices to study. Okay, this is something which is very useful, this lemma. So suppose you have a matrix whose entries are given like this, fxi, xj, where f satisfies this property, same as what kn satisfies. This is called integrating out lemma. Then what you can do, if you integrate with respect to xn, remember the last row and column will contain xn. If you integrate this thing, you will get some constant times the n minus 1 minor. So you have a n cross n determinant. If you integrate with respect to xn, which lies in the last row and last column, you have some constant times the n minus 1 minor. This is called integrating out lemma, and we'll use this. So we know that this kn xy satisfies the assumption of this lemma, right? It satisfies this kind of formula. And so first, let's determine what is this constant. So note that kn xs, if we integrate with respect to r, so let's recall what is kn xx. So, okay, I can write here. So remember that kn xy is e to the power minus n vx, e to the power minus n vy, summation pix, piy, I equals to 0 to n minus 1. So when I take x equals to y, we get e to the power minus n vx, summation come outside. Since x equals to y, this becomes pkx squared. What is this? What is this integral? Since pkx are orthonormal polynomials, this is 1, and we are taking a sum, so this is nothing but n. So the lemma above implies that this constant is n minus n plus 1. How can we use this? So we know that Rn, the nth correlation function, is some constant, and we're integrating the p function, right? And remember, I have written p function as a determinant. Oh no. Okay. So what I'll do, I will do repeated integration. So first I'll integrate with respect to xn. Some constant will come outside. Then I integrate with respect to xn minus 1. Some constant will come outside. And eventually I will get this. So you can see that this and this will cancel, and we get determinant of Jn. Okay. So now let's try to simplify more. So let's see the first correlation function. First correlation function is n factorial over Zn factorial, determinant J1. What is determinant J1? It is nothing but Kn xx. Okay, what I'll do now, I'll integrate this thing. As we have noticed that integral of Kn xs is n. Integral of R n1x is also n. So using this, we get that Zn double prime is nothing but n factorial. So this whole thing is 1. And so eventually I get that this nth correlation function can be written like this. So it is determinant of Kn xi xj. Okay, I wanted right after this before, but it doesn't seem I can write. So let me say in words. So what we have done, we have shown that correlation functions can be written as determinant of some function xi xj. So you can see it just suffices to study this function Kn xy. And so if you know the behavior of this function for large n, you can tell the behavior of Rn, this correlation functions, and that suffices to study many properties. Okay, this example was a part of general scheme. So I don't know, you might have heard something known as determinantal point processes. So this is exactly what it is. So, okay, let me say in words what is point process. So point process is something you can understand, like suppose you have points on real line and they are distributed randomly, like in this case. So we have n eigenvalues and they are distributed randomly on the line. So this is a point process. And for every point process, you can define something known as correlation functions. And if those correlation functions can be written like this form, they are called determinantal point process. And actually there's a theory on determinant point process, and you can like go after, like you can just follow that. And this becomes very easy once we have shown that this correlation functions can be written like this. Okay, I think, yeah, यहीं पे खत्म करते हैं. लैपटॉप साथ नहीं देगा मेरा. Yeah, sorry.